Okay, so this is problem 1.9 out of Griffith's Quantum Mechanics textbook. Before I get into solving the problem, if you wouldn't mind please liking the video and subscribing, I would greatly appreciate that. So problem 1.9 is going to follow a pretty similar path for problems we've done before. We have to find a normalization constant, find some expectation values, work with Schrodinger equation, and now we're adding the uncertainty principle to this. So we'll start with part A. So this is just our normalization condition. So that's to say 1 is equal to psi star psi of the integral from minus infinity to infinity of psi star, which is just going to be e to the minus a mx squared over h bar minus it times e to the minus a mx squared over h bar squared plus it. Okay, dx. And if you wanted to, what you could do is simply combine your terms here. The integral from minus infinity to positive infinity. Your imaginary part essentially just goes away, and you're left with minus 2a mx squared over h bar dx. And this is an even function, so what we can do here is this trick, which I've done before. Hopefully you're okay with this by now. Just a little calculus trick here to make the integral a little simpler. And this is, you can find these integrals in the textbook, you can find them on an integral table. The result you get from this is, I'm just going to rewrite it here, 1/2 the square root of pi 2 am divided by h bar. I'm not going to work through these integrals just because the video would be very long. That doesn't look right. If this is something you really just want to know, like how they worked out the integral, like if there's a special request, I can do that, but I think most people are okay accepting like that's just a table integral. But anyways, obviously you can see that the 2's drop, and here we can solve for our normalization constant just by multiplying and dividing everything over. Then you get 2 am over pi h bar, square root of the square root, so this is to the power 1/4. Okay. Part B is a little different than what we've done before, but we're going to use our Schrodinger equation, which I have conveniently here, which is to find the potential energy that is a solution to the Schrodinger equation. Okay? And what we're going to do is we're going to look at our wave function here, and we're going to take derivatives with respect to time once and with respect to position twice. Okay? So I'm going to actually see if I can just rewrite this out really quick. So psi is a constant a, which we just found, e to the minus a, and then mx squared over h bar, and then minus it, or plus it. Okay. So, and you could imagine using your e to the minus a mx squared over h bar. So just using our properties of exponentials, e to the minus a I t. That'll actually make this a little bit easier. So if you want to take the derivative of our wave function with respect to time, this part is just all constant. So you're really only taking the derivative of that part. And when you do that, you just get an additional minus a e to the minus a m x squared over h bar times a I, and then you get your other exponential back, which if you notice is just minus IA times your wave function, our original wave function. But our Schrodinger equation also has to do with the second derivative of x. So we need to find dy dx. And now, in this case, I don't know why that's there. The a is obviously a constant, and this is now a constant because we're taking the partial with respect to x. So when we do this, that's minus 2, well, we have our a, but we'll do minus 2a m a over h bar. And then you just have e to the minus a m x squared over h bar, and our constant e to the minus I at. And this is also can be written as 2a m over h bar times your original wave function. Okay. Also, there should be an x here because you have, when you take the derivative of the top, it's 2x. So there should be an x here. There we go. But our wave function is in terms of the second derivative of our wave function. Our Schrodinger equation is written in terms of the second derivative of our wave function with respect to position. So we're going to have to do this all over again, but that's fine. Notice now that while there are still a lot of constants, I'll just factor those all out right now. We still have x e to the minus a m x squared over h bar. So I'm just going to do this part right here. This is obviously a product rule, so derivative of the first times the second, plus, so when we take the derivative of our e, well, we'll just get, first off, we have our first function. So we'll have 2, we have x times minus a m x squared over h bar e to the minus a m x squared over h bar. So this just becomes a minus. This becomes now x cubed. So that times all of this, 2a m little a e to the minus a I t over h bar. And then we have to multiply with that derivative that we just found, which is e to the minus a m x squared over h bar. We're supposed to go away. Minus a m x cubed over h bar. E. Did I forget the 2 again here? I believe I did. I believe there should have been a 2 here. I don't know why I keep forgetting that. So just writing everything out here. Okay. So we have all of this. And let's see if there's any way we could maybe rewrite this. Let's see, we'll keep our normalization constant in terms of A. But let's see, I noticed that there is this common term here. So I could factor that out, and that looks promising because I'll show you why. Oops, that's not what I want. minus 2a m little a over h bar. What was our wave function? Right there, perfect. Minus a m x squared over h bar e to the minus ait, 1 minus 2a m x cubed over h bar. And you might notice that we get our original, that was just our original wave function psi. So that is good. We have minus 2 ma over h bar times 1 minus 2am. I believe that should be x squared. What did I do here? Yeah, this should have been, I think I did the square, but I didn't include the 2. That should have been, these should be 2's. Went a little too fast with taking the derivative, because the derivative is 2x times x will be 2x squared. Okay. Let me write this h bar a little nicer. It's bothering me. 2x squared over h bar times our original wave function. Okay. So now we're ready to plug everything into our Schrodinger equation. I'm just going to rewrite it here. Sorry, this one's a little longer. I don't know if there was a quicker way of doing this other than just skipping a lot of steps. Which I'm trying to, I saw a poll a lot of you didn't like that I would do that. So I'm trying to not do that for some of you that prefer it. So now we can just substitute everything in and solve for your potential. So you have v times your wave function is equal to I h bar times minus IA psi plus h bar squared over 2m times minus 2ma over h bar times 1 minus 2 ma x squared over h bar times psi of x comma t. All right, so just dropping our wave function here. That's why we wrote it that way. We have our potential. Let's see, I squared is -1. So minus I squared, that's just going to be h bar a plus h bar squared over 2m times, let's go ahead and I guess distribute minus 2m a over h bar plus 4m squared a x squared a squared over h bar squared. Just making sure I did that correctly. 4m squared a squared. Yep. So then our potential h bar a plus, I'm going to distribute this now, and you just get, well, I guess that's going to be a minus h bar a, and then distributing this, you can see you get plus 2m a squared x squared over h bar. Okay, so actually there is no h bar there. There we go. So these obviously go away, and then your potential energy is 2m a squared x squared. So this potential energy is the solution. Okay. So that was a lot longer. C and D, I think, will go a lot faster. So we'll start with just finding our expectation values. And again, the expectation value of x is equal to this integral. And we're going to have module a squared e to the, what was it again, minus 2am x squared over h bar, minus 2m a x squared over h bar dx, and then times x. An odd function times an even function is an odd function over that symmetric interval is 0. So that's fantastic. X squared, we're going to do essentially the same thing. I'm just going to, first off, it's going to be an even function now, because an even function times an even function is even. So I'm going to do the same integral trick here. X squared e to the minus 2m a x squared over h bar dx. So this is just a matter of solving for your integral using integral table integration by parts, kind of up to you, but what you end up getting is 2a squared times 1 over 4 1 over 8 am over h bar pi h bar over 2am, and plugging in for what we know a to be and solving, you get h bar over 4am. Okay. Now we also need to calculate the expectation value of momentum. We can use what we used in a previous problem, that the expectation value of momentum is just defined like this. And since the expectation value of x is 0, the expectation value of the momentum is 0. To find the expectation value of momentum squared, so this one we're going to have to be careful with. H bar over I, putting in the operator. D by dx psi dx. Okay. So put in the complex conjugate, put in the wave function, obviously the h bar I, and the a also can come out. That's not affected by the derivative at all. And you have e to the minus, I think it's just an a, x over h. Let me just write it up here real quick and check. Where's our wave function? Okay, so we do this, but with a minus sign there. So e to the minus a m x squared over h bar minus it. Did I get all that right? It's an x squared. Yep. Just double checking. Yeah. So you have this, and then you need to take the second derivative of e to the minus a mx squared over h bar plus it dx, and this is the second derivative. Let me make sure I didn't write down the complex conjugate. Yeah, that's just the wave function, so we'll switch the sign. Fantastic. So take a derivative of this twice. You'll get some stuff you need to integrate. Long story short, when you do all of this, your expectation value of momentum is just going to be a m h bar. Okay, so it's just really calculus at this point. Take a couple derivatives. You might be able to do U sub, you might be able to do parts, you could just throw it into a calculator, and you end up getting this. So now for part D. Part D is wanting us to find its relation to the uncertainty principle. So sigma x squared is defined like this, right? And we know that this was just 0. So then this is equal to h bar over 4am, which tells us sigma x is just the square root of this. And then we can do something similar for sigma p. Once again, this was 0. So this is equal to just a m h bar, with squaring both sides. That just gives us the square root of a m h bar. So our uncertainty principle is sigma x times sigma p, which is h bar times a m h bar over 4am square root. The am's obviously cancel, and this is going to be equal to h bar over 2, which is consistent with the uncertainty principle. Okay. So hopefully that makes sense. This was a little bit of a longer video. Part A, just find the normalization constant, nothing crazy. Part B, a little bit longer, a lot of derivatives, but hopefully it made sense. C, also a lot of calculus, and then D is showing that what we found is consistent with the uncertainty principle, which it was. Hopefully that makes sense. If it did, please like the video and subscribe.